Okay, so next we're going to bring all of this together with a few concrete examples. The first one is we'll consider the function f of x is equal to x to the 4 minus 4x cubed on the interval from 0 to 4. So for each of these examples, our task is to locate the maximum and minimum values. So we want to identify all of the critical points. We want to identify what the endpoints are. We want to identify which critical points or endpoints are local minima or local maxima, inflection points, and then use the second derivative test where possible, and then see what the whole thing looks like. So first, we're going to start by taking the derivative. F prime of x, 4x cubed minus 12x squared. Simple enough. So the first step after taking the derivative is to look for critical points. And to do that, well, in fact, we're taking the derivative in order to search for the critical points. So the critical points are where the derivative is either undefined, which we don't have a problem with here, or where the derivative is equal to 0. So we want to set f prime of x equal to 0 and see what values of x can make this equation true. So that means 4x cubed minus 12x squared is equal to 0. So this is just f prime of x right there. We're setting it equal to 0. Now oftentimes when you're doing this, looking for critical points, it's very beneficial to factor out any common factors that you have in the derivative. And this also comes into play with exponentials and product rule things, which we'll see in a bit. But just whenever you have the derivative, try to factor it as best as you can. So in this case, a 4 factors into both terms, and an x squared does. So let's pull out 4x squared. So it's 4x squared times x, and then minus, we're left with 3. So now this makes it much clearer. We have a critical point when x is equal to 0 and when x is equal to 3. Those are our two critical points. So already the only possible places where we can have a maximum or minimum are at the points 0. Let's do something. Since that's the endpoint, I don't want that to be the endpoint. Let's broaden this domain -2. -2 to 4. So that way, we have an actual critical point inside our domain. It makes it a little bit more interesting. So with this modified domain, the only places where we can have a local maximum or minimum are at -2, 0, 3, and 4. Those are our 4 candidates. Now the second derivative test can be used at the points 0 and 4, but it can't be used at -2 and +4. We can just look at the derivative and say, well, what's the derivative when x is equal to -2? Or what's the derivative when x is equal to 4? And then if the derivative is positive, well, we can see what happens as a result of that in a moment. Do it directly. So let's look at f prime of -2. F prime of -2. I'm doing a little bit different. I'm not actually straight out evaluating the function. So f prime of -2 is going to be negative. I can see this right away. I don't need to know what it is. I just need to know if it's positive or negative, and it is negative. I know this because when I plug in -2 for x, I get x cubed. -2 cubed is going to be negative. -2 squared is going to be positive, but this term has a minus in front of it. So it's going to be a negative number minus a positive number. A negative minus something is still going to be negative, so f prime of -2 is negative. So when this domain starts at -2, whatever the y value is, it starts with a negative derivative, which means it starts off decreasing. So -2, local maxima, local minima. So we'll put -2 as a local maximum. And let's do the same trick at the point x is equal to 3. So at 3, we have f prime of 3. We get 3 cubed times 4 minus 12 times 3 squared. We can't do that trick because it's a positive minus a positive, so that might be positive or negative. So 3 cubed times 4, so that's 27 times 4, minus 12 times 3 squared is 9. Ooh, it's 0. Oh, of course it is. That's not the end point, that's the critical point. So it's a good thing that that's 0 because it's a critical point. We found the point x is equal to 3 because of we looked for points that satisfy the equation x prime of x is equal to 0. The point I was thinking about was 4, f prime of 4. Okay, 4 times 4 cubed is 4 to the 4th, 256, minus 12 times 4 squared, this is going to be positive, 64. This board's a little bit sensitive, it's always resizing itself and doing some weird things. Okay, so f prime of 4 is 64, definitely greater than 0. So that means that we hit the point 4 and it has a positive slope, so it's increasing. So that means 4 must be another local maximum. Well, that's weird because we have a maximum, so let's say that they alternate, a maximum, minimum, maximum, minimum. So that's weird that we have a maximum on both of these, but we'll see in a moment what's happening. So let's use the second derivative test. Since we're doing this indirect, we're not actually evaluating the function at these 4 points. Let's use the second derivative test. Actually, let's take a quick moment and just evaluate. F of minus 2. So f of minus 2 is going to be 16 plus doesn't make sense. 2 cubed is 8 times 4 is negative 32, or 32 with a minus sign, plus 16, negative 16. So f of negative 2 is negative 16. F of 0, that's our first critical point, is 0. F of 3 to the 4th is 81 minus 4 times 3 cubed is negative 27. Negative 27, and f of 4 to the 4 minus 4 times at 4 it's just going to equal 0 because 4 to the 4 minus 4 times 4 cubed is the same as 4 to the 4th minus 4 to the 4th, which is going to be 0. So we basically have something like this. Okay, negative 16, 0, negative 27, 0. So it's a little bit weird. What's happening? Well, it looks like this one, you would suspect that it would look like this. But in fact, I see where I made a mistake here. F of minus 2 is not negative 16. I forgot about the sign here. Negative 2 cubed is negative 8. The negative and the negative makes it positive 8 times 4 is 32. So we get 2 to the 4th, which is 16 plus 32, not 16 minus 32. So it's 16 plus 32. So that's 48. So we have 48, so it's way up here. So it's weird, we have something up here. Why does it keep doing that? We have 48 up here, so it's easier if you just look at the dots, because that's really all we have. We have a dot up here, so it's a little bit weird. So maybe this is a maximum, which we said earlier. This one's a maximum. Maybe this one is neither. So let's use the second derivative test just to see, because it's not like it's going up, down, up, down, up, down. It's up, down, down, up. So probably it levels out but is neither a max nor a min at the point 0. So let's take a look and see if we're right. So the second derivative in general is going to be 12x squared minus 24x. So the second derivative at the point 0 is 0. So okay, the second derivative test is indeed inconclusive, so that supports our claim that the point 0 is a critical point, but it's neither a maximum nor a minimum point. And then f double prime of 3, just to confirm that that's actually a minimum, 3 squared is 9, 9 times 12, and then minus 24 times 3. So the second derivative, f double prime of 3, is 36, greater than 0. That means it's concave up, which means it's a minimum. So 3 is our local minimum. So that's exactly what the graph looks like. So we had our point up here at -2. It comes down like this, and then it continues to swoop up, and then it goes up like that. So that's exactly what our graph looks like. So now let's go to another example. So let's analyze the function f of x is equal to ln of x over x squared on the interval from 1 to 3. So obviously our boundary points 1 and 3 are two possible points where we might have a local maximum or a local minimum. F prime of x, okay, we're going to have to use the quotient rule. The quotient rule says that the derivative of the quotient, so we'll call the numerator the top, and then the denominator we call the bottom. So the derivative of the quotient is the bottom times the derivative of the top, x squared times 1 over x, and then minus the top times the derivative of the bottom, all divided by the bottom squared. So remember, it's bottom times the derivative of the top minus the top times the derivative of the bottom. So we have this, the order that we do this matters, because otherwise we'll get the sign wrong. So here we have x squared times 1 over x, that's x, minus 2x ln of x over x to the 4. So the derivative is the same as 1 minus 2 ln of x over x cubed. So the derivative, the x cubed will always be positive because we're between 1 and 3. So we're looking for when the derivative is equal to 0, because those are our critical points. So the derivative is equal to 0 when the numerator is equal to 0. So the derivative is equal to 0. So f prime of x is equal to 0 when 1 is equal to 2 ln of x, or when x or ln of x is equal to 1/2, or x is equal to e to the 1/2. So the derivative is equal to 0. Our critical point is when x is equal to e to the 1/2. Now let's just see where that is approximately, make sure it's on our domain. So yeah, so that's approximately at 1.648721271. So approximately at x is equal to 1.64872. So now let's try to figure out whether it is a local minimum or a local maximum. So f prime was 1 minus 2 ln of x over x cubed. F double prime of x is going to be the bottom times the derivative of the top. Now the derivative of the top this time is 2 over x, actually with a minus. So bottom times negative 2 over x. So that's negative 2 over x. And then minus the top times the derivative of the bottom. So 3x squared times the quantity 1 minus 2 ln of x, all over the bottom squared, which is x to the 6th. Okay, x cubed over x is x squared. I have an x squared here. The x squareds cancel with that, so we get minus 2, minus 3, this factors in, and then plus 3 times 2, 6 ln of x, all over x to the 4th. So this is the same as minus 5 plus 6 ln of x over x to the 4th. Now, when x is equal to e to the 1/2, ln of e to the 1/2 is just 1/2. So 1/2 times 6 is 3. 3 minus 5 is negative. So f double prime, so the upshot is that f double prime of e to the 1/2 is less than 0. Less than 0, concave down, this point is a local maximum. So probably what our function looks like, something like this. So the local maximum is going to be at, probably the global maximum is going to be at e to the 1/2. And to find out which one's a global minimum, we have to just evaluate the original function at both points 1 and 3. So, okay, so, all right, so here's the derivative and here's the second derivative. Just do it like that. This is f double prime of x. Okay, so f of 1 is ln of 1 over x squared. Now ln of 1 is 0. F of 3 is ln of 3 over 9. And that's a positive number. So the global min must be at x is equal to 1, and the global max is going to be at x is equal to e to the 1/2. So I know I'm basically concluding that e to the 1/2 has to be greater than ln of 3 over 9. So let's just check that out. E to the 1/2, when I plug in e to the 1/2. Well, e to the 1/2, take the ln divided by e to the ln, e to the 1/2 squared. So f at e to the 1/2 is approximately 0.183939721, whereas f of 3 is going to be ln of 3 divided by 9, 0.122. So that confirms 0.68032. So that confirms that e to the 1/2 is the global maximum. I knew it was the global. The second derivative test only tells me it's a local maximum. I knew it was global because it's the only critical point, and then we have just 2 endpoints. So if it's the local maximum and there's just 2 endpoints on the sides, it must have been the global max as well. So there's one thing we'd like to do with this problem, and that is find the inflection point. So recall that the inflection point is the point at which the second derivative is equal. Actually, that's not true. It's not when the second derivative is equal to 0. It's when the second derivative changes sign. So an inflection point is when f double prime changes sign. So it's when you have a change of concavity. So when it goes from concave up to concave down. So that's the inflection point right there, inflection. And so if it's an inflection point, the second derivative has to be 0. So let's take a look at the second derivative and set it equal to 0. So f double prime of x equals 0. Well, the bottom is going to be positive, so it's just up to the numerator to be 0. So that implies that -5 plus 6 ln of x is equal to 0. So set 5 equal to 6 ln of x, divide by the 6. 5, 6 equals ln of x, so x is equal to e to the 5 over 6. 2.3. So that's at approximately 2.300975891. So there's a change of concavity at approximately this point. So we had the point 1, and then e to the 1/2, that's about 1.6, and then up here at 3 we have this point. But between the e to the 1/2 and 3, at e to the 5, 6, we have a change in concavity. So it looks like it's probably going from concave down to concave up. So you get an inflection point at e to the 5 over 6 That's your inflection point. And this probably just levels off and goes to 0. So that's what that function looks like.